String theory is certainly not a well-established theory. It's not like the standard model of particle physics, or like Einstein's theory of gravity.
Indeed, the journey from the early days of quantum mechanics to the quest for a theory of everything has been filled with fascinating developments and challenges. Einstein's reluctance to fully embrace the probabilistic nature of quantum mechanics. As famously expressed in his quote, "God does not play dice with the universe," reflects the profound conceptual shifts required by this revolutionary theory. Schrödinger's cat, Heisenberg's uncertainty principle, and the exploration of quantum superposition all push the boundaries of our understanding of reality at the smallest scales. However, reconciling these quantum phenomena with the gravitational forces described by general relativity has proven to be a formidable obstacle. Loop quantum gravity emerged as one attempt to bridge the gap between quantum mechanics and general relativity, offering a discrete, granular description of spacetime. Despite its promise, a fully coherent theory that unites gravity with the quantum realm remains elusive. Enter string theory, a bold and ambitious framework that proposes that the fundamental building blocks of the universe are not point-like particles but rather tiny, vibrating strings. String theory seeks to encompass both quantum mechanics and general relativity within a single, unified framework. However, it has faced criticism and encountered significant mathematical and conceptual challenges. Edward Witten, a leading figure in theoretical physics, has made substantial contributions to both string theory and quantum field theory. His insights have shed light on the deep connections between different areas of physics and inspired new avenues of research. As we continue to explore the frontiers of theoretical physics, the quest for a theory of everything remains one of the most profound and tantalizing puzzles of modern science. Whether string theory ultimately proves to be the pathway to this grand synthesis or if a new paradigm shift is needed, only time and further investigation will tell.
String theory is the framework in which humans have been able to imagine how quantum mechanics and gravity can work together consistently. It's a long-term speculative enterprise. We only understand aspects of it even after decades of work. Personally, I think that having discovered how quantum mechanics and gravity can work together consistently, it's our duty to explore it more. If string theory had not been discovered, I personally think that I would not have tried to discover something like it, because I would have had no idea where to begin in reconciling quantum mechanics and gravity. But it's kind of unnatural to ignore the fact that there's an extremely rich theory that people actually have discovered that can make this work. And it doesn't just make it possible for gravity and quantum mechanics to work together, but it forces them upon you. If you start trying to use string theory to describe a quantum theory that you think maybe doesn't have gravity, gravity is literally forced upon you because of the way it pops out of the equations.
The comparison between quantum field theory, QFT, and string theory provides a fascinating journey through the intricacies of theoretical physics, reflecting the quest for a unified understanding of the fundamental forces governing the universe. This exploration delves into the historical context, theoretical frameworks, contributions of prominent physicists like Edward Witten, and the challenges posed by alternative approaches. Quantum field theory, QFT. Quantum field theory stands as one of the most successful frameworks in theoretical physics, providing a robust description of 3 out of the 4 fundamental forces: electromagnetism, weak nuclear force, and strong nuclear force. At its core, QFT treats particles as excitations of underlying fields that pervade spacetime. These fields, such as the electromagnetic field or the quark field, are quantized according to the principles of quantum mechanics, giving rise to particles as quanta of these fields. QFT has been instrumental in elucidating various phenomena in particle physics, from the behavior of subatomic particles to the interactions between them. Through the exchange of force-carrying particles, or gauge bosons, QFT explains the fundamental forces as arising from interactions between these underlying fields. However, despite its remarkable success in describing the 3 non-gravitational forces, QFT encounters significant challenges when it comes to incorporating gravity into its framework. General relativity, which describes gravity as the curvature of spacetime caused by mass and energy, resists straightforward quantization within the confines of QFT. Attempts to reconcile gravity with the principles of quantum mechanics have led to theoretical inconsistencies and the quest for alternative approaches. String theory. String theory represents a radical departure from the particle-centric view of quantum field theory. In string theory, the fundamental constituents of the universe are not point-like particles but rather one-dimensional strings. These strings vibrate at different frequencies, akin to the harmonics of a vibrating guitar string, giving rise to a diverse spectrum of particles observed in nature. The revolutionary aspect of string theory lies in its potential to unify all fundamental forces, including gravity, within a single theoretical framework. Within the framework of string theory, the graviton, a hypothetical particle mediating the gravitational force, emerges naturally as one of the vibrational states of the string. Thus, string theory offers a promising avenue towards a quantum theory of gravity, which has long eluded physicists. String theory's mathematical elegance and potential for unification have sparked considerable interest and research within the theoretical physics community. Its ability to encompass both quantum mechanics and general relativity has made it a leading candidate for a theory of everything, aiming to provide a unified description of all fundamental forces and particles in the universe. Edward Witten's contributions. Edward Witten, a towering figure in theoretical physics, has made seminal contributions to both string theory and quantum field theory. His insights have illuminated the deep connections between seemingly disparate areas of physics, mathematics, and even philosophy. Witten's work has played a pivotal role in advancing our understanding of string theory and its implications for fundamental physics. His research has shed light on the mathematical structure of string theory, the emergence of new symmetries, and the interplay between string theory and other branches of physics. Witten's contributions extend beyond theoretical physics, encompassing diverse areas such as quantum field theory, topological quantum field theory, and mathematical physics. His profound insights have reshaped our understanding of fundamental concepts in physics and inspired new avenues of research. Challenges and alternative approaches. While string theory offers a compelling framework for unifying fundamental forces, it has also faced criticism and skepticism. Critics argue that string theory's predictions are difficult to test experimentally, leading to debates about its validity as a fundamental theory of nature. The lack of experimental confirmation has prompted physicists to explore alternative approaches to quantum gravity. One such alternative approach is exemplified by the work of physicists like Jonathan Oppenheim, who proposed departures from the assumptions of string theory. Oppenheim's research suggests a classical view of gravity, avoiding the need for quantization and addressing fundamental issues such as the black hole information paradox. These alternative approaches challenge the conventional wisdom in theoretical physics and highlight the ongoing quest for a deeper understanding of the fundamental forces governing the universe. While string theory remains a leading candidate for a unified theory of physics, the exploration of alternative frameworks underscores the richness and complexity of the quest for a theory of everything. In summary, the comparison between quantum field theory and string theory illuminates the profound challenges and remarkable potential inherent in the quest to unify the fundamental forces of nature. Whether through string theory or alternative approaches, physicists continue to push the boundaries of knowledge, seeking a comprehensive theory that elucidates the mysteries of the cosmos. Thank you for watching another episode of Space Odyssey. While you are still here, don't forget to like and subscribe.